Hold an apple in your hand, feel its weight, its smoothness, the subtle give when you press your thumb against its skin. This simple fruit sitting in your palm seems solid, real, finite. But what if I told you that within this apple lies a mystery so profound that it touches the very fabric of reality itself? What if we could zoom in deeper and deeper past what our eyes can see, past what any microscope has ever revealed, into realms where the rules of existence itself begin to dissolve? The question isn't just whether we can keep zooming in forever. The question is, does the universe even allow such a thing? What we're about to discover will change how you see everything around you, because at the smallest scales imaginable, reality becomes something far stranger than anyone could have predicted. Let's begin this journey together, you and I, standing here with our apple. We know what it looks like from the outside, red perhaps, or green, with that characteristic shape that has nourished humanity for millennia. But we're not content with surfaces. We never have been. From the moment our ancestors first looked up at the night sky and wondered what those points of light really were, we've been driven by an insatiable curiosity to look deeper, to understand what lies beneath. So let's do what humans do best. Let's ask, what happens if we keep looking? Imagine we have a microscope, but not like any microscope that exists today. This is a device limited only by the laws of physics themselves, capable of revealing whatever the universe permits us to see. We begin our descent into the small. At first, the journey is familiar. We zoom past the surface of the apple's skin, and we see cells, those remarkable little factories of life that make up all living things. Each cell is a universe unto itself, filled with structures and machinery more complex than any factory humans have ever built. There are membranes, nuclei, mitochondria, the powerhouses that convert nutrients into energy. These cells are perhaps 50 micrometers across, about half the width of a human hair. Already we've shrunk our view by a factor of thousands. But we're just beginning. We zoom further past the cell walls, past the cellular machinery, and we enter the realm of molecules. Here we find the building blocks of life, itself long chains of carbon, hydrogen, oxygen, nitrogen, all arranged in patterns of breathtaking elegance. We see proteins folding into precise three-dimensional shapes, DNA coiled like a twisted ladder, carrying the genetic instructions that made this apple what it is. These molecules are measured in nanometers, billionths of a meter. We've shrunk our perspective by another factor of thousands. But notice something remarkable. We're still seeing structure, still seeing organization, still seeing things that appear to have definite shapes and boundaries. Press on, zoom deeper still. We pass through the molecules and arrive at individual atoms. And here, for the first time, we encounter something truly strange. An atom, you see, isn't really a thing in the way we usually think of things. It's not a tiny billiard ball, solid and impenetrable. An atom is mostly empty, space vast, incomprehensible emptiness. If you could expand an atom to the size of a football stadium, the nucleus at its center would be smaller than a marble sitting on the 50-yard line. Everything else, that entire stadium would be empty, except for a few electrons, those ghostly particles that don't even have a definite position until you try to measure them. The nucleus itself is extraordinary. Packed into that infinitesimally small space are protons and neutrons, held together by forces so powerful they can overcome the natural repulsion between positively charged particles. This is the strong nuclear force, one of the four fundamental forces that govern our universe, and it operates only at distances smaller than an atomic nucleus. We're now at the scale of femtometers, quadrillionths of a meter. To give you a sense of scale, if an atom were the size of Earth, the nucleus would be about the size of a football field. We've journeyed from something we can hold in our hand to something so small that the very concept of size begins to lose meaning. But we're not stopping. Our imaginary microscope keeps zooming, and now we pierce into the nucleus itself. Inside the protons and neutrons, we discover something even more fundamental, quarks. These are among the smallest things we know of, the apparent building blocks of matter. A quark has never been seen in isolation. They're always bound together in groups, held by particles called gluons. And here's where things get interesting, because we've arrived at a scale where our everyday intuitions about how things work completely break down. At this scale, the universe operates according to quantum mechanics, a description of reality so counterintuitive that even the scientists who pioneered it never fully made peace with it. Now, you might be thinking, surely we can keep going. If we've made it this far from apples to quarks, why should there be any limit at all? Why can't we just keep zooming in forever, revealing smaller and smaller structures, turtles all the way down, as they say? This is where we encounter one of the most profound insights in all of physics, and it's an insight that speaks to the very nature of reality itself. There is a limit. Not a practical limit, not a technological limit, but a fundamental limit written into the laws of nature. It's called the Planck length, and it's approximately 1.6 times 10 to the negative 35th meters. To put that in perspective, if you could expand the Planck length to the size of a grain of sand would expand roughly the size of the observable universe. It's not just small, it's almost impossibly small, at the very edge of what the word small can even mean. Why does this limit exist? The answer lies in the marriage of two great theories of physics, quantum mechanics and general relativity. Quantum mechanics tells us that at very small scales, everything becomes uncertain. You cannot simultaneously know both the exact position and the exact momentum of a particle. This is Heisenberg's uncertainty principle, and it's not a limitation of our instruments. It's a fundamental property of reality. The more precisely you try to measure where something is, the less you can know about how it's moving, and vice versa. This uncertainty becomes more pronounced as you zoom into smaller and smaller scales. General relativity, Einstein's theory of gravity, tells us that mass and energy warp the fabric of space-time itself. Now, here's the crucial insight. When you try to measure something at incredibly small scales, you need incredibly high energies. Those high energies have mass equivalents, remember? Einstein showed us that energy and mass are two sides of the same coin. And if you concentrate enough energy into a small enough space, general relativity tells us that space itself begins to curve dramatically. At the Planck scale, the energy required to probe smaller distances would be so enormous that it would create microscopic black holes. The very act of trying to measure something that's small would fundamentally alter what you're trying to measure. Space and time themselves would become turbulent, foamy, quantum. Think about what this means. There may not be anything inside a quark, not because we haven't looked hard enough, but because the question itself might not make sense. At the Planck scale, our usual notions of space and time break down. It's not like looking at a fuzzy photograph where you wish you had better resolution. It's more like asking what's north of the North Pole. The question assumes a framework that doesn't apply. This is humbling, isn't it? We're accustomed to thinking that every question has an answer, that every door we open reveals another door behind it, but the universe is under no obligation to arrange itself according to our preferences. The Planck length represents not the limit of our technology or our imagination, but possibly the limit of how finely divided reality itself can be. Below this scale, the smooth continuum of space-time that we experience in our everyday lives may give way to something else entirely, something discrete, quantized, fundamentally granular. Yet there's something deeply beautiful about this. For thousands of years, philosophers wondered whether matter could be divided infinitely or whether there were fundamental, indivisible units. The ancient Greek philosopher Democritus proposed the existence of atoms, literally meaning uncuttable, as the smallest units of matter. He was both right and wrong. Right that there are fundamental scales to nature, wrong about where those scales are. We've journeyed far beyond Democritus's atoms, through molecules and atoms and nuclei and quarks, and we may finally be approaching the actual limit. What's fascinating is that the same kind of limit appears when we zoom out, not in. If we travel outward from our apple, past Earth, past our solar system, past our galaxy, past the entire observable universe, we encounter another fundamental limit. The universe is finite in time. It's about 13.8 billion years old, and light can only travel so far in that time. Beyond the age of the observable universe, there may be more cosmos, but we can never see it because the light from those distant realms hasn't had time to reach us yet. So in both directions toward the infinitely small and the infinitely large, we find boundaries, limits imposed not by our tools, but by the nature of reality itself. This raises profound questions. If the Planck length is real, if space-time itself is fundamentally granular at the smallest scales, what does that mean for our understanding of the universe? Some physicists believe that space and time are not continuous, but made up of discrete units like pixels on a screen. If you zoom in far enough on your computer monitor, you stop seeing smooth curves and start seeing individual dots of light. Could the universe be similar? Could there be a smallest possible unit of space and a smallest possible unit of time? These aren't just academic questions. They touch on the deepest mysteries of physics. How do we reconcile quantum mechanics with general relativity? What happened at the very instant of the Big Bang, when the entire universe was compressed to scales smaller than the Planck length? What happens at the center of a black hole, where matter is crushed to infinite density? All of these questions require us to understand physics at the Planck scale, and we don't yet have a complete theory that works there. String theory, loop quantum gravity, and other approaches all attempt to bridge this gap, but we're not there yet. We stand at the shore of a vast ocean of ignorance, and that's exactly where science becomes most exciting. Consider the poetry of our situation. We are collections of atoms arranged in such a way that we can contemplate atoms. We are made of quarks and electrons, and yet we can discover quarks and electrons. We are the universe looking at itself and finding that there are limits to what it can see. This doesn't diminish us, it elevates us. Despite our cosmic insignificance, despite being tiny creatures on a tiny planet orbiting an average star in an ordinary galaxy, we have managed to probe the deepest secrets of nature. We have looked into the atom and seen the quantum world. We have looked out into space and seen the expansion of the universe. We have asked profound questions and found real answers. But perhaps most importantly, we've learned that there are questions we cannot answer, not because we're not clever enough, but because the universe itself may not contain the answers. The Planck length teaches us humility. It reminds us that for all our knowledge, for all our technological prowess, we are still bound by the same laws that govern everything else in the cosmos. We cannot zoom in forever because forever may not exist, not in the way we imagine it. And yet, this limitation doesn't stop us from wondering. It doesn't stop us from asking what lies beyond. Even if we can never directly probe the Planck scale with our instruments, we can still reason about it, still build theories, still push the boundaries of human understanding. That's what we do. That's what makes us human. Every answer we find leads to 10 new questions. And in that endless cycle of discovery lies the beauty of science. So here we are back to our apple, same hand, but now you see it differently. You know that within it lies layer upon layer of structure, from cells to molecules to atoms to quarks, each layer governed by different laws, each revealing new wonders. You know that this journey inward has a limit, that there's a smallest scale where the very concepts of space and time begin to dissolve. And you know that somehow, impossibly, we've figured this out. We've taken the universe apart, piece by piece, and discovered not just what it's made of, but the limits of what can be known. The question was, can you keep zooming in forever? And the answer, as far as we can tell, is no. But that no is not a dead end. It's an invitation to understand why, to explore the boundaries of knowledge, to marvel at a universe that is both comprehensible and mysterious, both knowable and fundamentally strange. The Planck length is not a wall that stops us. It's a signpost pointing toward deeper truths we have yet to discover. We live in a universe of limits and possibilities, of questions and answers of the known and the unknown. And somewhere between the apple in your hand and the Planck scale quantum foam at the heart of reality lies the story of everything, the story of matter and energy, space and time, life and consciousness. We are part of that story, you and I. We are the universe's way of knowing itself. And what a privilege that is to be able to ask these questions, to seek these answers, to stand in awe of the cosmos and our place within it. The journey from the everyday to the Planck scale is not just a journey through space. It's a journey through understanding, from the familiar to the bizarre, from certainty to mystery. And while we may never zoom in forever, we can forever keep asking why. In the end, that might be the most human thing we do.